Hey there, this video is a continuation from the last video. In the last video we did problem set 35, which is about enthalpy, and now we're doing the continuation of that, which is problem set 36. The goal of these problem sets is to learn how to calculate the delta H of a reaction. Okay, there are multiple ways to calculate the delta H, or the enthalpy change, of a reaction. Okay, one, which we treated in the last video, and we'll talk a little bit about it in this one too, is to use Hess's law. And that essentially says I have component reactions that add up to my desired reaction. If I can get those component reactions to add up to my desired reaction, then the delta H's of those component reactions will add up to the delta H of my desired reaction. So that's Hess's law. Two is using delta H's of formation. We'll talk about what a formation reaction is, but essentially if I have the enthalpy of formation, which is the heat associated with forming a certain compound, then I can calculate the delta H of my reaction by summing up the delta H's of formation of my products, because I'm forming my products, so I want to use the delta H formation of my products, and then subtracting the delta H of formation of my reactants, because I'm not forming my reactants, I'm unforming them, and so I want to use the negative value of the delta H of formation of my reactants. Okay, and so pretty much what I'm doing is, when I'm using delta H formation, I'm pretending that I'm taking all of my reactants and unforming them, splitting them into elements, and then taking those elements and reforming my products. Okay, so I'm going to use the delta H formation of my products, the negative delta H formation of my reactants, and since delta H's of formation are in kilojoules per mole, I'm going to multiply each of these by N. You're going to see what this looks like as we do some examples. But remember that enthalpy is a state function. So basically what we're doing here with Hess's law is we're saying I have my reactants and I have my products, and I want to get this delta H, but instead I'm going to use one reaction to get to those compounds, and I'm going to use a different reaction to get to these compounds, and a different reaction to get my product. Then I'm going to use the delta H's of these and add them up to get my total delta H. Well, with delta H's formation, what I'm doing is I'm saying I have my reactants, I have my products, I'm trying to get the delta H from the reactants to the products, so I'm going to pretend that I take my reactants, I split them into pure elements in their standard state, which we'll talk more about that, and then I take those pure elements and I reform my products, and I use the delta H's there, and add up those delta H's to get my total delta H. Now if I'm going from pure elements to products, that's the delta H's of formation. If I'm going from reactants to pure elements, that's a negative delta H formation. So that's why I end up with delta H formation of my products and negative delta H formation of my reactants. Okay. The last way that we talk about is using bond enthalpies. Okay, with bond enthalpies, I'm doing something very similar. I got my reactants, and I've got my products, and I want to get the delta H from my reactants to my products. And instead of splitting them into pure elements, so pure elements could be like O2. That's a pure element in its standard state. Instead of doing that, I'm going to break them into individual atoms and recombine those atoms into products. Essentially, I'm going to break every single bond in my reactant compounds so that I'm just left with atoms, individual atoms, and then I'm going to reform every single bond in my products. So what we do is we use bond enthalpies, which is the energy required to break a bond. So I'm going to use the bond enthalpies. So I'm going to sum up the delta H's of my broken bonds, because the bond enthalpies is the energy to break a bond. So all the energy required to break a bond. I'm going to subtract the delta H, the bond enthalpies of the formed bonds. Okay, and again, I'll have moles there. We'll see examples of all of these. But bond enthalpies is the delta H to break a bond. So I want to use the delta H for the bonds I break. That's these, breaking up my reactants. And then since bond enthalpies is the energy to break a bond, I'm going to use the negative value of the energy to break a bond for all of those things that are formed. Because I'm not breaking those bonds, I'm forming those bonds. All right, so these are the three ways that we talk about calculating the delta H of a reaction. You can use pure Hess's law when we give you component reactions. We can use delta H as a formation, or we can use bond enthalpies. A lot of people like to ask the question, well, how do I know which one to do? That should be pretty clear based on what they give you. If we give you component reactions, use Hess's law. If we give you delta H as a formation, use delta H formation, products minus reactants. If we give you bond enthalpies, use bond enthalpies, broken minus formed. So let's go through some of these, and hopefully your questions can be answered. So, first question, for which of the following does delta H reaction represent a heat of formation? Well, heat of formation, that's just delta H of formation. So really all this is asking is, for which of these is the delta H of the written reaction equal to the delta H of formation? In other words, which of these is a formation reaction? Well, what's a formation reaction need? You need to form 1 mole of something from pure elements in their standard states. So I can go through this. A forms 1 mole, and it forms it from elements in their standard state. So that's a formation reaction. So the delta H of this reaction is equal to the delta H of formation of CO2, because I'm forming CO2. All right, B forms 2 moles. Automatically not a formation reaction, because a formation reaction only forms 1 mole. Plus, it forms it not from elements in their standard state. Here's an element in its standard state, but this is a compound, so this is not a formation reaction. Here we're forming multiple compounds, not a formation reaction. Here we form 1 mole from elements in their standard state, so that is a formation reaction. So the delta H of this reaction equals the heat of formation of CH4. Here I form 2 things, so not formation. Here I form 2 moles from elements in their standard state. But I can only form 1. So the delta H of this reaction is equal to 2 times the delta H of formation of NO. Okay, so this is not a formation reaction, it's double formation reaction. What would the formation reaction look like for NO? Well, I'd be forming 1 mole of NO from elements in its standard state. I need to balance this, so I need 2 N's. So can I put a 2 there? No, because then it wouldn't be a formation reaction. That's what I have right here. We just agreed that was not a formation reaction. I can only form 1 mole. So the only way to balance this would be to put a half there and a half there. And that's just fine. That would then be a formation reaction. But that's not what this problem has, so that's wrong. Here I form 1 mole, but it's not from elements, so that's not a formation reaction. And here again, I form 2 moles, not a formation reaction. So we're left with just A and D in this case. Okay. That brings us to number 2, Hess's Law. So this is process number 1 that I talked about at the beginning. 1 second. Okay. Hess's Law can be used to find standard enthalpies of formation. PbO is the key component of automotive lead acid battery and is also used extensively in making lead glass. SiO2 doped with PbO, whatever. Write a balanced equation for the standard enthalpy of formation of PbO. All that means is write the formation reaction for PbO. Okay, that's the first part of this problem. Formation reaction PbO, I'm going to write it right here. You're making 1 mole of PbO from pure elements in its standard state. So my elements are Pb and O2. And to balance this, I need 1/2 O2. Then it says calculate the standard enthalpy of formation using the following information. So I'm using these equations. I get some of these weird figures when I convert the PDF to a text file. So let's see. Hopefully that's not important because I don't know what it is, and these should be deltas. Instead they turn into houses with X's on them, but it should just be a delta H. All right, so essentially we're trying to find the delta H of formation of PBO, right? Well, that's just the delta H of this reaction. Because it's a formation reaction, the delta H of the reaction equals the delta H of formation of PBO, because that's what I'm forming, right? So they give me component reactions, so that means I should be using Hess's law, and I should be using these reactions to try and create my formation reaction. So I've got PB on the left. Here I have PB on the right. So I know that I'm going to need to flip that top equation. So I'm just going to flip it right now. PB plus CO goes to PBO plus carbon. Now, I don't want this delta H because I flipped the reaction. So the delta H of this new reaction will be negative 107 kilojoules. And now I don't care about this one anymore because I flipped it. All right, so now I've got PB on the left. I've got PBO on the right. Now I need oxygen on the left. Here I have oxygen on the left. Awesome. But I have one oxygen and I need half an oxygen. So that means I'm going to take this reaction, multiply the whole thing by a half. That means this goes away, and this becomes a half. It also means that this delta H becomes half of what it was. There we go. So now I've got my half O2 taken care of. Now everything else should cancel out, does it? Yes, I have a carbon graphite here. That I don't care about. And a carbon there I don't care about. I have a CO here I don't care about. And I have a CO here I don't care about. So all I'm left with is the PB plus 1/2 O2 goes to PBO, which is exactly what I want, which means that the delta H's of these two component reactions will add up to the delta H of this reaction that I just made. So the delta H of that is negative 111 minus 107, which is going to be negative 218 kilojoules. So since this reaction is the formation reaction for PBO, the delta H of this reaction is going to be the delta H of formation of PBO, which is exactly what it asks us to find. Now part B. CaCO3 is the main component of seashells. Write the balanced reaction for the standard enthalpy of formation for CaCO3. Balanced equation for the standard enthalpy of formation. All that's asking is to write the formation reaction for CaCO3. So let's do it. I know I'm making CaCO3 from its elements in its standard state. So my elements are going to be calcium, and I've got carbon, and I've got oxygen, which in its standard state is O2. One calcium, one carbon, 2 oxygens, 3 oxygens, which means I need 3 halves of this. 3 halves O2 is just 3 oxygens. So here is my formation reaction for CaCO3. Calculate the standard enthalpy of formation using the following information. They give me this reaction, which has the delta H of that reaction given. Then they give me the delta H of formation of this and the delta H formation of this. They want us to find the delta H of formation of this guy. Well, am I going to use Hess's law where I flip around equations and stuff like I did in part A? No, because they don't give me equations to flip around. And what they give me is delta H's of formation, which means I'm going to want to use, why don't I just drag this down with me? They give me delta H's of formation, so I want to use this guy. I know that the delta H of a reaction equals the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants, all multiplied by their mole values, which is just the coefficients in the reaction. Okay, so for this reaction, they give me the delta H of the reaction. Okay, so I know that delta H reaction is 178.1 kilojoules. And that's going to equal the delta H of formation of CaO plus the delta H of formation of CO2, those are my products, minus the delta H of formation of CaCO3, my reactant. Well, I have this, they give me this, they give me this, they ask for this. So I can just plug all of these guys in. 178.1 kilojoules equals negative 635.5 kilojoules plus negative 393.5 kilojoules minus delta H of formation of CaCO3. And I get that the delta H of formation of CaCO3 equals negative 1207.1 kilojoules. So here they give me delta H as a formation, so I use my delta H of formation method. And I wasn't finding the delta H of the reaction, right? They gave me that. I was finding one of the delta H's of formation, in this case of a reactant. All right, CuO is a pigment in ceramics and is involved in the process of making rayon. Write the balanced equation for the standard enthalpy of formation. Hopefully you're noticing a pattern here. That's just the formation reaction for CuO. Well, I'm making 1 mole of CuO from elements in its standard state. And calculate the standard enthalpy of formation using the following information. So here they give me a reaction, they give me the delta H of that reaction, they give me the delta H of formation of something in there, which means I'm probably going to be using enthalpy of formation values. So I know that the delta H of a reaction equals the sum of the delta H of formation of products minus the sum of the delta H of formation of reactants. They give me the reaction, negative 129.7. Let me write this out even more. Delta H of the reaction is going to equal, what are my products? Cu and H2O. My products minus my reactants are CuO and H2. All right. Now, they give us this, they give us this, they ask for this. What about these guys? Well, this is an important piece of information to know. If I were to write the formation reaction for H2, I'd be forming H2 from elements in their standard state, which is just H2. So what's the delta H of this reaction? Well, the delta anything of this reaction is going to be 0 because there's no change. H2 to H2, no change. So delta H of this reaction, 0, which means the delta H of formation for any element in its standard state is 0. So without giving it to you, you know that this is 0 because copper is in its standard state, and that's 0 because hydrogen is an element in the standard state, which means I don't need those values because I just know them. So delta H of this reaction is negative 129.7 equals the delta H formation of water, which is given, now, it says kilojoules per mole. I just wrote kilojoules because technically I'm multiplying these delta H formation numbers by the number of moles in the reaction. And there's only 1 mole here. So technically I'm multiplying that negative 285.8 by 1 mole, so the moles in the bottom goes away. And then subtract delta H of formation of CuO. And I get that the delta H of formation of CuO is equal to negative 155.8 kilojoules per mole of CuO. Okay, calculate delta H for the combustion of ethanol to form carbon dioxide and water using the heats of formation below. So they give me, sorry, some of the text there is kind of weird, but it'll be okay. I'm trying to find the delta H for the combustion of ethanol. Well, what is the reaction for the combustion of ethanol? Let's write it. I got C2H5OH. If I'm combusting something, I'm adding oxygen, and I'm making CO2 and water because it says carbon and hydrogen on it, so I'm going to make CO2 and water. Now I got to balance this. Now if I'm writing the delta H combustion, I've got to only combust 1 mole. Similar to how if I'm writing the formation reaction, I've only got to form 1 mole. So 2 carbons, so I need 2 carbons there. I've got 6 hydrogens, so I need 3 there to give me 6. Gives me a total of 4 oxygens plus 3, 7 oxygens, so I'm going to have a 7 halves right there. I did that right? Oh, not quite. So I need 7 oxygens, but there's already an oxygen there, so I only need 3 here. Okay, so the delta, and I want the delta H of this reaction because this is the combustion reaction for ethanol, so the delta H of this reaction is the delta H of combustion of ethanol. Well, they give me delta H as a formation, so that's the method that I'm going to use is the products minus reactants method. So I know the delta H of this reaction is going to be the sum of N times the delta H of formation of my products minus the sum of N times delta H of formation of my reactants. Well, that's just my products are, so that's 2 times the delta H of formation of CO2 plus 3 times the delta H of formation of water. Those are my products. Minus 1 times the delta H of formation of ethanol plus 3 times the delta H of formation of oxygen. Okay, they want this. I'm given delta H formation of ethanol, delta H formation of CO2 and water. I'm not given this one, but remember this is a pure element, O2, so that's just 0. So the delta H of this reaction is just going to be 2 times delta H formation of CO2 plus 3 times delta H formation of water minus 1 times delta H formation of ethanol. All right, and you can see that this is kilojoules per mole times 2 moles, so the moles will cancel and all these will just be kilojoules added together. Plugging that in my calculator. And I get the delta H of this reaction, which again is just going to be the delta H of combustion of ethanol, because this reaction is the combustion reaction of ethanol, is just going to equal 1366.7 kilojoules. And I could write kilojoules for the reaction, or I could write kilojoules per mole of ethanol, because the reaction is burning 1 mole, but either of those makes sense. Okay, let's keep going. Fertilizer, which is ammonium nitrate and fuel oil, a mixture of long-chain hydrocarbons similar to decane, can form an explosive mixture. Determine the enthalpy change in the following explosive reaction by using the appropriate enthalpies of formation from Appendix 4 in your book, and delta H of, and then they give you the delta H formation of this because it's not in your book. Okay, so they tell you to use enthalpies of formation, so we're going to be doing products minus reactants. So the delta H of this reaction is going to equal delta H formation of my products, so 3 delta H of formation of N2 plus 17 delta H of formation of water plus 10 delta H of formation of CO2 minus my reactants, 3 delta H of formation of NH4NO3 plus 1 delta H of formation of C10H22 plus 14 delta H of formation of O2. So I know the N2 is going to be 0 because it's a pure element. I know the O2 is going to be 0 because it's a pure element. And it tells me to look up the other ones in the appendix. Well, I'm not going to go that far because I have water and CO2 right here, which takes care of water and CO2. They give me this one in the problem, so it's really just that guy I have to look up in the appendix. But let's write this out. Delta H of this reaction is going to be, oh, that's 0, 17 times water. Water is going to be negative 285.8. CO2 is negative 393.5 minus NH4NO3. If I look that up, let's see, there it is. Negative 365.6, and then plus 1 times, they give me 249.7. Alright, so I can plug all that in my calculator. If I plugged it all in right, I should get the right answer. My mistake. I accidentally used the value for water as a liquid when in the reaction water is a gas. So I shouldn't have used 285.8. I should have used negative 241.8. So now if I go back and plug it in, and that's more like it. Okay, I get that the delta H of this reaction would then be negative 7198.5 kilojoules. Does it make sense that it's negative? Yeah, because it says it's an explosive mixture. So if it blows up, it should be releasing heat. All right, bond enthalpies. So in this case, they're giving us bond enthalpies. So your mind should be saying, okay, we're probably going to be doing that third process that we talked about at the beginning, which is the idea of using broken bonds and formed bonds to calculate the delta H's of a reaction. Okay, use the bond enthalpies in the table above to estimate the enthalpy change of a reaction below. Okay, so I've got N2H4 splitting up into N2 plus 2H2. So I'm given bond enthalpies, so I'm going to say, just as I've got right here, bond enthalpies, delta H of reaction is bonds broken minus bonds formed. So the delta H of this reaction is sum of N times enthalpy of bonds broken minus the sum of N times enthalpy of bonds formed. So what bonds are broken here? Well, I break an NN single bond, and I break 4 NH single bonds. What bonds are formed? Well, I form an NN double bond, or sorry, triple bond. Oh. And I also form 2 HH single bonds. So now I can just jump back to my table and figure out what's an NN single bond. 163, and that's in kilojoules. And an H single bond, 391. NN triple bond is 941. HH single bond is 436. Okay, calculate all that out. When I do that, I get the correct answer that the delta H of this reaction is equal to negative 86 kilojoules. All right, use the bond densities above to estimate the delta H reaction for ethane with oxygen gas to form carbon dioxide and water. That's just the combustion of ethane. So ethane is going to be C2H6 plus O2 forms CO2 plus H2O. I only want 1 mole of this, so then that's going to give me 2 of those. I'm going to need 3 of these, which that leaves me with 7/2 of that. Okay, so if I want to figure out which bonds are formed and broken, I'm going to have to draw out the Lewis structure, the Lewis structures here. So I'm going to have C. I'm going to make this smaller. So I'm going to need a lot more space. C2H6 looks like this. O2 looks like that. CO2 looks like this. And H2O looks like that. All right, so so what am I breaking? I am, sorry, I'll turn that off so you don't have to see about my Thanksgiving plans. All right, so the delta H of this reaction is going to be bonds broken minus bonds formed. So I am breaking 1 CC bond, 6 CH bonds, and 7/2 OO double bonds. Does it make sense to break 7/2 of a bond? Can't break half a bond, right? So it doesn't really make sense, except that I'm using all of these values as moles. So it's really 7/2 moles of a bond, and you can have half a mole of something. All right, so that's what I'm breaking. And what am I forming? Well, I'm forming 4 CO double bonds, and I'm forming 6 OH bonds. So I've got it here. So a CC is 348. A CH is 413. An OO is 495. CO double bond 799. And an OH bond is 463. It's always a miracle if I can plug this into my calculator and get it right the first time. So I guess this time it's a miracle. So I get that the delta H of this reaction is negative 1415.5 kilojoules. All right, that brings us to part C, where we're going to use the bond enthalpies in the table above to estimate delta H reaction for the following reaction. Chlorine gas with ethene forms 1,2-dichloroethane. All right, so they tell us to use bond enthalpies, so we're going to do the same thing. We're going to have broken minus formed, so what breaks? Well, we've got a CC double bond that breaks. We've got 4 CH bonds that break. And we've got 1 Cl-Cl single bond that breaks. That's just these guys. And what forms? I have 2 CH bonds that form. And I have, 4 CH bonds that form. And I have 2 CCl bonds that form. Okay, so CC double bond is 614. CH is 413. Cl 328. CH again is 413. CCl is 328. A lot of people recognize that you've got 4 CHs broken and 4 CHs formed. Those will just cancel each other out, right? So you could not include them, but I'm going to. And I realize I just forgot. I also have a CC bond there. And the CC single bond is 348. Okay, let's do the math. And this should be a negative. Don't know why I wrote positive. Okay, I'm getting something wrong, so let me see where I can. So CL. Oh, a CL is 242. I was using the value for CCl. Did that do it? Yeah, that did it. Okay, so that gives me that the delta H of the reaction is negative 148 kilojoules. Okay. Use bond enthalpies to estimate delta H of the reaction for the Haber process below, in which nitrogen from the air is fixed into a usable form. Compare this with delta H reaction calculated from delta H of formation. So basically they're saying that delta H of formation of NH3 is negative 46.19. This reaction, is this the formation reaction for NH3? No, it's twice that. Right, because I'm forming 2 moles from pure elements. So delta H of this reaction should be 2 times the delta H of formation of NH3. So they're just asking us, let's use bond enthalpies to calculate the delta H of this reaction and see how that compares to the actual delta H formation. So what's breaking? Well, this is N2, this is H2, this is NH3. So I'm going to have broken, I'm going to have an N triple bond, I'm going to have 3 HH single bonds. And what's formed? 6 NH single bonds. Why? Because I've got 3 here and 2 NH3s. All right. All right, and then triple bond, 941, HH is 436, NH looks like it's 391. Which got me -97. So the delta H of this reaction equals -97 kilojoules. How does that compare? Well, based on the delta H of formation, which is -46.9, the delta H of this reaction should be 2 times -46.19, which is -92.38. Yep. And we got 97, -97. So why is this off? Which is more accurate? Bond enthalpies is less accurate. And the reason is we say that an HH bond, well, that's not a good example, an NH bond is 391 kilojoules. Well, an NH bond in one molecule is going to look different than an NH bond in a different molecule. And so these bond enthalpies are really the average value, so the average energy to break an NH bond. And so as a result of that, this value is a little bit, has some error in it compared to this value. So that's why they're not exactly the same, and the delta H formation values are more accurate than bond enthalpies. All right, interesting real-life problems. Listed below are the molar enthalpies of combustion for several fuels. These fuel values provide a measure of energy available to harness by burning the fuel. However, since we don't purchase fuels by the mole, we purchase them by mass or volume. A better way of comparing them is to use a fuel value. Fuel value is simply the heat of combustion in units of kilojoules per gram instead of kilojoules per mole. Calculate the fuel value for each of the following compounds from their heats of combustion and state which fuel has the highest energy density. Okay. It's interesting that they ask about the energy density, because energy density is so let's see, fuel value is kilojoules per gram. Energy density is kilojoules per liter, and the only way you'd be able to find that is if you had actual densities for each of these, and they don't give you densities. So I'm going to say that you can't actually find that. But we can figure out what has the highest fuel value. So let's do it. So they give us -286 kilojoules per mole. They want kilojoules per gram. Well, it's hydrogen, it's H2. That means that 1 mole is 2 grams. So that gives us a fuel value of -143 kilojoules per gram. But in real life, in industry, anytime you're burning a fuel, the delta H is going to be negative. And because if you are a race car driver, you don't care about the direction of the heat flow, fuel values are almost exclusively written as positive values. So I'm just going to write 143 kilojoules per gram. Okay, so for each of these, really all we're doing is dividing by the molar mass. So in this case, 802 kilojoules per mole. 1 mole is 16 grams, and that gives us and again, I'm going to write it as the positive value. That's how we write fuel values. And again, this is just because it's not very useful if we are trying to compare fuels to compare them by mole amounts, because nobody in the real world talks in terms of moles. They talk in terms of mass. And I'm copying these molar masses and these answers off of the key, just because I don't want to go through and actually calculate out the molar mass of all of these. And so if there's computational errors or a molar mass error on the key, then it's going to be in this video as well. But hopefully you understand that all I'm doing for each of these is dividing by the molar mass of the fuel. Alright, so if I look at these, the thing with the highest delta H of combustion is butane. Okay, but the thing with the highest fuel value is, oh wait, is this a 5 for octane? Yeah, that's a 5. Okay, so really the highest then is octane. But that's not the highest fuel value because octane is heavy. So the highest fuel value is actually hydrogen. And that results from multiple things, but mostly just because hydrogen is so light. Anyway, so that is problem set 36 about enthalpy. Again, the main points that you should be taking from this is the 3 different ways that we can calculate the delta H of reaction. We can use Hess's Law, which manipulates component reactions. We can use delta H's formation, where you just do products minus reactants, or we can do bond enthalpies, where we do bonds broken minus bonds formed.